So now it's my pleasure to introduce the first speaker who will be talking about MapReduce and its sort of innovative applications. Abhishek Chandra has come here from the University of Minnesota to give a presentation. He is a professor in the School of Computer Science and Engineering there, and he has been producing pioneering work on MapReduce, and he'll now tell us about that. Thank you. You have to get rid of it.
Okay, thanks, Jeffrey. Thanks for the introduction. So today I'm going to be talking about running MapReduce in non-traditional environments, and I'll come to what I mean by non-traditional environment in a short while. But at the beginning, let me give you a brief outline of the talk. First, I'll talk about some of the high-level motivation and the big picture about the landscape, in particular big data and how MapReduce fits into it. And again, you may have been hearing about some of these things yesterday, and you'll continue to hear about some of these next few days as well. So I won't necessarily belabor the point too much. Then I'll give a little bit of background on MapReduce because that would be needed to understand the later part of my talk. And again, there would be much more details about MapReduce and Hadoop in particular that you will be hearing about later today in other talks as well. So this is not meant to be comprehensive by any means. Then I talk about some of the ongoing research that we are doing at the University of Minnesota, where we are looking at running MapReduce in slightly different kinds of environments that what traditionally has been used in the past. In particular, traditionally MapReduce has been deployed in tightly coupled clusters with dedicated machines and centralized data stores, etc. And I'll be talking about environments where you may have much higher amount of distribution, in particular geographically distributed data sources, geographically distributed computational resources, and so on. And then finally, I'll conclude my talk. Okay, so as many of you are aware, we are living in the age of big data. There's a lot of hype behind big data, but a lot of the hype is actually real. There's a lot of data being generated by enterprises as well as different communities. The data is coming out both from user end, where users themselves are producing a lot of data, or services that are directly facing the users are generating a lot of data. Think of services such as Google, Gmail as the easiest example to think of, as well as a lot of data that is being generated at the back end, either from scientific instruments or from enterprise workloads, and there's a large amount of log data out there which also has a lot of useful information. So there's a lot of data coming out in all different domains, commercial, social, scientific, and so on. And again, typical examples include big companies such as Google, Facebook, Yahoo, or big scientific instruments such as the Large Hadron Collider, but there's data being generated in all spheres of life. So having a lot of data is useful, but you need to be able to extract information out of it and then convert that information into knowledge. Only then is the data going to be useful. So data analysis is beginning to play a very important role in how decisions are made in all these different spheres of life. So the large amount of data has led to a need for scalability and parallelism if you want to be able to do data analysis in a meaningful and efficient way. This basically means dealing with terabytes and petabytes of data, very large number of files, several thousands of nodes in order to extract their parallelism as well as to extract the computing power. And then also a lot of the data is being generated and consumed by millions of users. So there's scale in all these different dimensions. In addition, you also need to do data analysis in a cost-effective and reliable fashion. In particular, that might mean using commodity hardware instead of dedicated supercomputing machines or specialized hardware, in order to carry out the computation. Now, if you are using commodity hardware, that means that failure now becomes a norm. So you also have to make your system slightly reliable so that you can do any meaningful computation. In addition, with the advent of cloud, there's also a drive towards sharing a lot of these resources among communities and users. So your systems have to be robust to be able to support large number of diverse users and applications. So this is where MapReduce comes in to help deal with this large quantity of data and to carry out large different kinds of meaningful data analysis applications. Now, what is MapReduce? It is basically a data parallel programming model and framework. So it provides ability for applications and users to scale up to large number of machines to extract their parallelism, and also to large number of disk and storage devices. In addition, it provides a fairly simple programming model which can be used by an average programmer to design a fairly powerful data analysis program and implement different kinds of data analysis algorithms. And it was pioneered by Google. They had started, proposed the MapReduce framework as part of the requirements that they had with respect to the large amount of data that they were handling, particularly for their web search engine. And now from there, it has really spread to a lot of different domains. Yahoo introduced the open source Hadoop project, which has now become sort of a very popular platform for many other companies and other users as well. And it's now being widely used in several different domains. So what is MapReduce good at? First of all, it's very good at scaling up to large number of machines and large number of disks. And it can handle terabytes to petabytes of data. That is good. In addition, it's designed to be fairly cost efficient across different dimensions. So it's cost efficient in terms of hardware because you can basically throw in commodity hardware. Basically, you can take a bunch of Linux boxes, put them together over your commodity network, and then you can fire up MapReduce and it's ready. It's also fairly cost efficient in terms of administration. First of all, it has inbuilt reliability and automated fault tolerance. So whenever a machine goes down, you don't have to rely on manual intervention to get the system back up and running. Okay. So that saves a lot of time and effort. In addition, it's fairly configurable, so administrators can pretty easily set it up out of the box and get it running. And finally, from a programmer's perspective, also it's fairly easy to use. It has a fairly simple programming model so that you can easily write an algorithm which captures the semantics that you are trying to implement in the system. And we'll talk about the programming model in a little bit of detail later. So where is MapReduce being used? It's being used almost everywhere. In the industry, the big players, places like Google, where they started by using it for their web search engine, where they used it to analyze a lot of the data that they were crawling over the web and converting it into the indices that were being used by the web search engine. And then they also use it for several other purposes, such as for clustering articles for Google News, etc. Again, Yahoo used it for several similar kind of applications, including web search, Yahoo Mail, etc. Facebook is using it quite a bit for things like ad optimization, spam detection, and a lot of other things as well. So there's a whole laundry list that you can put in there. MapReduce also has got a lot of attention in research and academia, especially for scientists who have large amount of data and they want to analyze that at scale. And there are a bunch of different projects going on at different universities, and here's maybe a very small list of all the different projects going on, including some work that's going on right here at Indiana as well.